Okay, back to the class. So let's talk about boosting. Again, I based these lectures on these slides on these books, and mostly I was using this one, which is a bit harder book, but they explain boosting better here than in this book. I should tell you right away that, like, as usual, when you will be using boosting in practice, you will be using, just say in Python, XGBoost. This is a usual library that everyone is using, super well implemented with lots of features. And most likely you will not be even thinking about what's happening. But you should understand how boosting works. It might matter in the future for your applications, depending on the applications, you should have an idea. And the same way as when you're doing a linear regression, you're just applying it without thinking about it. But hopefully you understand what's happening. Okay, we start with the most famous algorithm that started this whole literature. This algorithm is called Otherboost M1, or simply Otherboost. So originally, this algorithm was designed for classification problems, but we will be applying it mostly for regressions, and then we will see how it generalizes to regressions. So we deal with a, say, two-class problem with output belonging to -1, 1. And we giving a set of predictors x, like p-dimensional as usual, so it can be x1, xp as usual. A classifier should produce a prediction either -1 or 1. Then the error rate is simply the number of misclassified observations. Then the motivation behind the Otherboost is to combine many weak classifiers to produce a powerful committee. And weak classifier here is in the sense that its error rate is only slightly better than a random guessing. So the idea of this combining, this is what it means by boosting. The idea of combining many weak classifiers to produce one good, strong classifier, this idea goes back to like 80s. There was a paper in the 80s, I forgot by whom, but you can find it on Google, on the internet, who put forward this idea of boosting. And there was a important result at the time that if you have a series of classifiers that are slightly better than a random chance, then you can always combine them to produce one strong classifier with the needed level of precision. And vice versa. If there is one classifier with a given level of precision, a strong classifier, you can always write it down as a sum or a combination of a certain number of weak classifiers. Now, that was a theoretical result, and it's not clear at all how you can go back and forth. And this Otherboost algorithm was the algorithm that suggested how you can do this combinations of weak classifiers to get a strong classifier. So the idea, and I'm going to describe it here, and in the coming slides, is we keep modifying the data and keep applying a series of weak classifiers on the data and keep modifying our data, and eventually, hopefully, we get a strong classifier on the original data set. A sequence of weak classifiers is given by GM, and each of them is weak, meaning that each of them is slightly better than but potentially could be slightly better than a random chance, but not necessarily. So here's the schematic illustration of this algorithm. First, let's look at the picture. We start with the original training sample. We have a classifier on this training sample. Then we use this classifier to modify the sample, get a new sample that would be a weighted original sample, where original observations are given certain weights. Then on that weighted original sample, we construct a new classifier, modify the sample, give new weights, and so on. We start with the weights equal for each observation. Get each observation xi yi gets a weight originally 1n, where n is the number of observations, and then we keep modifying the weights. And the idea here is to give the most problematic observations on each stage. The most problematic observations get a bigger weight, so that we want to use the next classifier to more correctly classify the problematic observations, and we do it sequentially, iteratively. Then eventually we combine all these classifiers with some weights alpha, which are also an outcome of this algorithm, to produce the final classifier gx. And this number m, this is the important number. This is a hyperparameter. We need to choose it by cross-validation or by some heuristic. The larger is this number, the better we fit the data, but then we might be overfitting the data. If the number is small, then we don't fit the data well, so we can have a large bias potentially. When we are applying this classifier, suppose this number is 100 or like 200, which is not uncommon in practice, then we would have 200 weak classifiers, and when we fit like a new observation to these classifiers, we need to add up 200 values calculated through different classifiers. So in that sense, this can be computationally intensive to implement, but of course the existing implementations are quite efficient. Here's the algorithm of Otherboost as it was formulated in this original paper by Frond and Shapira, 1997. So we start with weights 1 over n, then we go through the m weak classifiers from 1 to m big. We fit a classifier to the training data using weights wi. What is this classifier? It can be anything, but in practice we use trees, and we will come to that in a second. But for now, this algorithm is a general enough algorithm that is just deals with any classifier. Then we compute an error, which is the misclassification rate on the data set adjusted for the weights. Then we compute the weight of this classifier, which is strangely given by this function. Then we recalculate the weights, where we apply this weight alpha m calculated here, and the indicator function if we classify this observation or not. If we classify it correctly on this observation on this iteration, then we don't modify the weight. Otherwise, we increase the weight. Then, as I said, output will be just a sign of the sum of these classifiers. So here's an example, a simulation example, when we have, say, 10 independent variables, so predictors drawn from the normal 0-1 distribution, all of them independently, and data generating process is for y is that y is equal to 1 if the sum of squares of this regressors is more than chi-squared with 10 degrees of freedom and parameter 0.5, which is equal to 934 and minus 1 otherwise. So the sum of 10 Gaussian random variables is distributed as chi-squared with 10 degrees of freedom. And then chi-squared 0.5 is the median value. And so we classify if the sum is more than half of the observations, basically, roughly half, we classify as 1, roughly half as minus 1, because this is the median value. Now, here we are using, as a classifier, we will be using a single stump, which is classification tree with just 2 terminal nodes. So, and this is not an uncommon thing in the Otherboost. And this will differ from GradientBoost. And I will try to emphasize it several times, the differences between Otherboost and GradientBoost. They sound the same, but they're different. So the single stump is the usual weak classifier used in Otherboost context. So, and this important thing to keep in mind here or to understand here is that a single stump means that even though we can have, so we have 10 regressors in this example, each time when we do a classification on each iteration of Otherboost, we choose only one regressor to do the split. And that would be our step. Then on the next step, we again choose only one. So in this example, we have, if we use a single stump, this would be the error. If we use, if we grow a 244 node tree, the way I described in the previous lecture, then that would be the error on the test data set. If we do then a boosting with the single stump, then on the one, first we get this error because we start with the single stump, but as we do boosting iterations, so here m is equal to 100, 200, 300, and 400. And so each time we apply a single stump, but we keep applying these iterations of Otherboost algorithm, and you see that it really outperforms the large tree, we get a much smaller error on the test data set. Now, that's, in a way, that's all that we need to understand about Otherboost algorithm, too bad. In a way, that's all we need to understand about Otherboost algorithm, the Otherboost algorithm. Now we are going to take a step back and talk about a more general approach, which is called Forwardstagewise additive modeling. And we will see that, we can see Otherboost as a particular case of Forwardstagewise additive modeling. So we can view boosting as a way of fitting an additive expansion in a set of elementary basis functions. So for the boosting for Otherboost that we have just considered, the basis functions are GM. More generally, basis function expansion takes this form, where B's are basis functions and betas are the weights or expansion coefficients. For the trees, so B's they depend on the values x, which is x1, xp, vector of features or regressors. And it's parameterized by a set of parameters gamma, which, say, in the case of trees, it's a variable that captures all the split or parameter that captures all the split variables and split points at all internal nodes and the prediction at the terminal nodes. So potentially for the boosting trees, for the just trees, this is this captures all of it. And if we think about a stump, just a tree with a single split, then the gamma would code which variable we used to do a split on. And the threshold value that we used for this variable, and the value that we assigned in each split for observations coming to that region. Left, right, like this. So that would be all recorded in gamma. Index k, threshold value t, and then left, right values. Then, but of course, we can have potentially any basis functions, but it's just boosting can be seen as just a particular example of fitting, constructing a model based on the basis functions. Then, usually when we do a basis function expansion, we usually are solving this problem. So forgetting for a second about Otherboost, just thinking about if we are dealing with minimizing some loss function by choosing parameters of base functions. This would be the problem that we would solve. We will be using the weights and parameters to minimize the loss on the observation yi, xi. And thinking back about what we talked about during the discussions of different approaches to forecasting. This is the classical approach to forecasting, which is sample analog approach. So if we're applying a sample analog approach, then we're solving this problem. If we're applying a sample analog approach based on the basis function expansions, then this is the problem that we solve. Now, this problem is very difficult, especially when we're working with trees. But in general, this is a very difficult problem. Even if we have a simpler basis functions, except for if this is something like a linear. This is a very usually difficult approach. And instead of using this approach, we use an approximation, which is a forward state called Forwardstagewise additive modeling. And during this approach, we add basis function expansion one by one. So the idea here is to sequentially add new basis functions to the expansion without adjusting anything that we have done up until that step. So we start, say, with the basis function this is not the basis, this is the forecast of prediction 0. Then we choose the number of steps, and on each step we minimize this loss function, taking this as given and choosing parameters beta and gamma on this step. Then we update the forecast by adding the forecast from the previous period and the basis function on that iteration from the previous iteration. Sorry, I misspoke. We update the forecast obtained on the previous iteration by adding the basis expansion of this iteration. So this is the idea of Forwardstagewise additive modeling. And if you think about the trees, this is a more formal way of writing this greedy approach of constructing trees. We optimize only at each step, at each iteration. We take what we have already done as given, we don't modify it, and we only add new things on each iteration. Now, it helps to think about Forwardstagewise modeling in terms of, say, squared loss, which is, if we're dealing with regression problems, this is the most commonly used loss function, right? So in terms of the squared error loss, this loss function would look like so. And then we can write it as this part minus this part. And we can denote this part as RIM, and we can call it the residual. And so we can view the stage-wise for the squared error loss. We can view stage-wise additive modeling as a way of improving the residuals by adding basis function, by doing basis function expansion on each iteration, we improve the residual. Okay, now if we are working with classification, then the quadratic loss, we know this is not a good loss criterion. And we need to consider other loss criteria. Now, just to go back to other boosting, that what we have achieved now, or we discussed now, we discussed Otherboost as it was introduced originally in this 1997 paper. And from my discussion of additive stage-wise modeling, you can already see that there is a similarity in the spirit of approach. Why we are talking about additive stage-wise modeling after we talked about Otherboost? Additive stage-wise modeling is a more general approach to doing classification or forecasting or prediction than Otherboost. And taking this more general view helps us to generalize Otherboost in different directions. Specifically, more importantly, also it allows us to understand better what's happening with Otherboost. So now we are going to talk about loss functions that are used in Otherboost. How Otherboost arises by the choice of the right loss function. And it turns out that if we use the exponential loss function in the stage-wise additive modeling, then we get Otherboost. Then the basis functions for Otherboost are the individual classifiers GM that we were using in the Otherboost. And again, in practice, it can be just a small tree or a stump. Then we can show, it's not obvious, but we can show that what is happening at each stage of Otherboost is minimization of this, of solving this optimization problem. And so Otherboost can be viewed as a particular example of stage-wise modeling, where we are minimizing this function. This is not obvious, and this needs to be a proof. We can, to prove this, we can rewrite the minimization problem as so, like the second equation here, where expression here, where we break this exponent into two parts, this part and this part. We denote this part by WIM, and this part doesn't depend on the classifier at the current step. So it doesn't depend on this. And we want to find this. We want to find G. Yi and Xi are the data, and we want to find beta and G. So weights already look like they're coming from Otherboost. If you look at the weights from Otherboost, then they kind of look like exponent of something. So it gives you an idea that, okay, it does look like we are minimizing this function. But it's still not clear because we don't know what this f is. We can solve this problem given the weights. We can solve this problem of finding beta and g in two steps. First, for any value of beta, we can find the classifiers. For that, we can rewrite this sum as the sum of, we take out the e to the power of beta minus beta, and then on our data set, we can divide the sum into two parts. One would be where yi is equal to our classifier, which yi, remember, belongs to minus 1, 1. Then if we get minus 1, minus 1, then their product will be 1. Similar, if we get 1, 1, then their product will be 1. And so their product, if we are correctly classifying, then the product yi and g will be a positive value, y. So we can, bring all such correctly classified values into one sum. And then for the incorrectly classified values, their product will be minus 1. So we bring them to the second sum and use here the positive value, because we multiplied here minus on plus. Then we can add to this sum epsilon yi and subtract. Then when we subtract subtract the same value, then combine this and these terms, we will get two terms. This term doesn't depend on g, and so what we really need to find, and this term doesn't depend on g, and it's positive. And so we really need to find a classifier that a g that solves minimizes this part, which is the classifier that minimizes the weighted error rate in predicting y, which is what we had in Otherboost. And then using the solution for g, the classifier, we can calculate the error. And you can see that then the value of beta that minimizes, say, this guy or this guy, the value of beta that would be minimizing this is simply equal to this. You can just differentiate this expression with respect to beta, assign it to 0, solve for beta, and you will get this. And so we basically get that that's the proof that we are dealing with, that indeed what we got is Otherboost. So to summarize, we have shown that stage-wise editing modeling approach with the exponential loss function is equivalent to Otherboost algorithm. Let me take, maybe I wasn't clear why we started talking about Otherboost. Because Otherboost was, when it was introduced, it was a very successful algorithm, and people, but then it was failing sometimes. And machine learning specialists were trying to understand what that algorithm was doing and why it was so successful. Why, especially why the algorithm was using particular weights, calculate like alphas and W's calculated using this and this, where they were coming from. And so then at first it sounded like a heuristic. Then specialists in machine learning understood, like 5 years later after the paper, in early 2000s, they understood that Otherboost belonged to a more general class of algorithms that are additive stage-wise modeling algorithm with particular exponential loss function. Once researchers realized this, they started wondering if the exponential loss function can be changed to get different, better, or some way result that are different in some ways. And also this understanding that Otherboost algorithm is just a particular case of stage-wise modeling algorithm with the exponential loss function led on generalization of that algorithm to an algorithm from classification to regressions by changing the exponential loss to quadratic loss. Now, the problem with both exponential loss and quadratic loss is that they're sensitive to outliers, meaning that outliers can lead to bad outliers in the sense that this is still part of your data set, because when you observe some, when in your data set you have an observation that whose values are way different from the rest, it's not like you should throw it away, because still it's a part of your data set. But that one observation can drive a lot of your prediction. And if it's a rare observation, then perhaps you shouldn't be putting too much weight on that observation. And the Otherboost algorithm, with its exponential loss, might be putting a lot of weight on that one observation, and so tending to make classification driven by that one outlier or a few outlier observations. And similar with regressions, with quadratic loss. That's where stage-wise modeling thinking in terms of stage-wise modeling helps, because now you can think, what are better alternatives to quadratic loss and to exponential loss? For the exponential loss, a better alternative can be binomial deviance, which I'm going to show in a second, while for quadratic loss, a better alternative can be an absolute deviation, absolute error. And that, however, using these different loss functions doesn't give such nice result algorithm that we have here. And that's where we need to start doing more work and thinking about how to solve this kind of procedure with more general loss functions. And that's where a gradient boosting comes in. So I skip this because this is a bit like advanced stuff, and you don't have to really know this. But I hope that, yeah, I want to show you the binomial deviance, which is a better alternative to uh, exponential loss. This is uh, the loss function based on the binomial deviance. You can check the slides or the book. Again, the book is available for free on the internet from the authors. So you can check the slides if you want to understand more. For me, what's more important here is that I want to show now how gradient boosting works as an improvement on the idea of stage-wise modeling. Let me pause here and see if you have any questions about what I've just discussed.
Uh, well, it's clear that um, Otherboost is just a particular case of stage wise. Well, yes, uh, of this area. But why do we need gradient boosting again? Like the
Yeah,
more what?
right, gradient boosting, because uh, we want to be able to work with more general loss functions, potentially. Another reason, so stage-wise modeling is a very general idea, and Otherboost is just one application of this idea with exponential loss. But again, what if exponential loss might not be the best loss? And then in the case of regressions, quadratic loss might not be the best loss because of the outliers. And in general, we might want to consider different loss functions, both for classification and for regression problems. And we cannot write them nicely the way we write it here, because if we have a more general loss function in this stage-wise algorithm, solving this problem might be difficult. It's clear how to solve this problem for exponential loss. I have just written to you. We can solve it analytically. And then we don't need to do any optimization. We just do iterations and all is fine. But what if we introduce, say, absolute value, absolute error as our loss function? Then this minimization problem is not differentiable. But well, it's kind of differentiable, but then it becomes not clear. It's not clear how to deal with this problem, and that's where we need numerical procedures, and that's where the gradient boosting comes in. But again, let me just emphasize here for a second that with such simple loss functions as absolute error, we still can write this algorithm in a nice way. But gradient boosting is a procedure that allows us to write this algorithm as a numerical procedure that can be applied to any loss function.
But talking about gradient boosting, are we still inside of forward stage wise modeling? or not?
Yes, that would
Okay.
be a kind of an improvement on forward stage, a numerical algorithm in the spirit of forward stage-wise additive modeling.
Okay.
Okay, so let's talk about gradient boosting and boosting trees. So before I discuss it, one remark that gradient boosting is also general in the sense that it doesn't have to use trees the same way as stage-wise modeling or other boosts don't have to use trees, but generally they generally use trees. Because they show, I mean, trees are the most simple way of doing it. So again, a little bit of the motivation about, behind the gradient boosting. Trees partition the space into region, as we saw before, and solve the regression. So now let's talk about the regression trees. They solve the regression problem by the rule, if X belongs to a particular region, then the prediction would be gamma J for this X, where gamma is the value assigned to that region. Then we can formally express tree as the sum of indicator functions weighted by gammas. And theta is the parameter of this tree, capturing the regions and gammas. Then the parameters are found by minimizing this function. So we are minimizing it across region by choosing regions and the gammas, the values, to minimize loss across all regions. The problem can be divided into two parts. Finding gammas for each region, this is easy. So if we already fixed the regions, then minimizing loss function across each region, we know how to solve this problem. This is what we do all the time. If it's a quadratic loss, then it would be mean. If it's a absolute value, then it would be median, and so on. But finding the regions is difficult, and we talked about it already. Now, what gradient boosting does, it applies again the stage-wise modeling idea of adding trees one by one that are solving loss minimization and keeping the previous predictor fixed, predictor obtained on the previous iteration fixed, and choosing a new tree. Now, as I said, if we have a squared error loss or exponential loss, then we have already seen how to solve this problem. This is easy. Especially, I mean, we have seen it for the exponential loss, but for the squared error loss, it's also easy. The problem is to choose the regions. And now what we will be doing, we will consider a numerical procedure that would solve this problem approximately. So if we use f, some function f, any function f, to predict y on the training data, then this is our loss. Then what we want to do is to solve the problem of minimizing the loss with respect to this whole vector of f, calculated on the values in the sample. In other words, we want to choose, our task is to choose non-parametrically a vector of values f that are corresponding to each observation. So for the first observation, we choose value of 1, for the second value of 2, and so on. And that will be our vector of values. Now, we can choose this vector of values by the steepest descent by calculating the derivative of this loss function with respect to each of this f1, f2, fn. And then that would give us so-called direction, or the steepest descent direction. So for each value of observation I, it will give you us the direction in which that loss function decreases the fastest. The higher is the derivative, the faster is the increase in the loss function. Then, in addition to that, we will choose the step in each direction, which will be the value. So the choice of these derivatives will give us a vector of g, which is a vector of derivatives. And then we will scale it up or down by parameter rho, which would like find the most, the best size at this stage. The role of this parameter is to find some average value that give us an average an average improvement in the loss. The thing is that the derivatives themselves, they can be either overshooting or undershooting the y's. And by parameterizing them with rho, the size of the derivative, we can be controlling this overshooting, undershooting on average. And so this general idea about how we can approximate the solution of this minimization problem given the trees. Now, the problem at this point is that it's all nice, but what we achieve with this is the fit of the function f at the set of points xi's, x1, xn. What we really want to do is to construct a function out of this. How are we going to do? We are going to apply trees to this. So we are going to be replacing this GIM, not replacing, but approximating it by fitting it by trees. By solving, say, for the quadratic loss, it would be solving this function, this minimization problem. why we are doing this again? Because that would be our nonlinear fit to the derivatives. Then, given this tree, we can now calculate its value in any x. And now it's a function. So we go from the derivatives to the function. Let me skip this and go over the gradient boosting algorithm steps. So we will the gradient tree boosting algorithm works like this. We start by minimizing the loss function by choosing just one value gamma. For example, if it's a quadratic loss, then gamma will be average value across all yi's, and f0x is going to be the loss. Sorry, it is going to be yi minus average y squared and sum. Now, after we initialized our algorithm with the average values, we start iterating. In each step, we compute the derivatives in the on the previous iteration by substituting previous iteration function f, which is our predictor. Sorry, I didn't say it correctly. Scratch it. Becoming too tired. F0x is just y average. Then we calculate our our r's derivatives. Say the first iteration by substituting the average value. If it's a say quadratic loss, then it would be equal. It is going to be equal to minus yi minus y bar at step 1 for m equal 1. Then we fit the regression tree to these residuals to construct a function that approximates these residuals or extrapolates these residuals. Then, for each region, we calculate the value that we are going to assign to that region by minimizing the loss function here. So if we are dealing with the quadratic loss, then it will be yi minus fm minus 1 calculated at xi plus gamma squared across all i's xi belonging to a particular region j. So for the solution of this problem would be average value of these guys, which would be average value of like residuals. And then we update our predictor by adding the values, the average values of residuals. And then we iterate. The same way as we iterate in stage-wise modeling or Otherboost, like 100 times or 200 times. And then our output would be this, the sum of all predictors. Now, let me stop here and I realize that this might be what I have just explained might be very difficult, or you might be lost, you don't understand what is going on, and it takes some time to absorb. And I should say that how I explained it, this connection with basis functions, Otherboost, connection to stage-wise modeling, then different loss functions. I followed these books that are usually cited as explaining as a source of the most thorough explanation of all these algorithms. If you Google gradient boosting on the internet, you will find several excellent resources that give you just step-by-step examples how it works. And I think I cannot do a better job than the examples that you can see on the internet. But again, my value here for you, I hope, is to explain you all these connections between different algorithms that are not necessarily explained well on the internet. Well, they explained in the textbooks. So I urge you to check up several videos. I think I can drop you the links that are the best that have the best explanations that I've seen. There are many explanations, but not all of them are equally good. I think the best one is this one, and the one from StatQuest. I dropped you a link on StatQuest before. Let me. One second. So check this as well. So these are the best sources on the internet that explain trees the best of all. And check the slides to understand all the connections between trees, Otherboost, gradient boosting, stage-wise modeling. And hopefully you will absorb everything after going through it a couple of iterations. And during tutorials next week, we will work with trees and gradient boosting. And we will work with the time series, apply these algorithms to time series. And hopefully, I hope that we'll have time to work with univariate models. Okay, let us finish here. Unfortunately, there is no time for me in this course to talk about vector autoregressions, but well, it was my first time to do lectures. Maybe if I ever do it again, I will do it better. Okay, that finishes today.
About exercise session. So we're not going to have them this Saturday.
Yeah,
We're going.
no session this Saturday.
Yeah, okay. But next week, as I can see it, it's like 20th of December. In our timetable, we have only one lesson with you.
Only one? I asked to put two.
Well, and strangely enough, just we have a lesson with you at like 11, and just after that we'll have another lesson, but like offline on campus. So you
Oh,
better connect with our study office to somehow.
okay. Thank you for letting me know. Yes, I will email about that. So you're saying that there will be some offline whatever class
Just
on
after
or
yours, yes. and
yeah,
uh,
okay.
and what is more like, if we're going to have two classes with you, I guess the first one should start at 9:30, because
Right.
at 1 p.m. we'll have another class offline. Yeah, it's strange, but that's how it is in our
Okay,
timetable.
okay. Yeah, yeah, okay. I will let them I will try to settle this issue. Right. So you're saying that in your timetable there is no class at 9:30 next week.
It is only at 11.
Okay, got it. Yeah, I will write. Okay.
If something, I have sent you the screenshot of our timetable in Discord.
Okay, yeah, thanks. That would help. Thank you very much.
And about vector outer regressive models, maybe you could recommend some links where to get acquainted, at least like, for the first glance.
Right. Yes. There are so many sources, I guess. Um, I will think about. I have a notebook prepared. I can show it during the tutorial. We will not have the time to go through it, but I can show you give you during the tutorial. Then you can look at it. But uh, they are explained in so many books. There are so many books devoted to them. It's very hard to find one resource. I've been following this book by, I always forget the names of the authors. Um, um, 1 second. Gizels and Marcelino. I've been using this textbook it's not a super good textbook, but I think VR explained relatively well in this textbook. So you can check it. It's on the syllabus.
Okay.
Okay.
Thank you. Goodbye.
Bye. You're welcome.